button right on the ribbon that just lets people say, I see your screen already before you even have to ask.
Exactly. We do this every meeting. So I just wanted to say hi. Thanks for coming to the community meeting. So this one here is probably going to be our, how many is it? It's at least 104th or 105th, something like that, meeting together. So what I'm showing on the screen here is last week, we closed 6 PRs. They had to do with these certain things. And then Ashutosh did a ton of work this last week, updating PRs around P4 limitations and BMV2 and just kind of trying to do a little cleanup behind the scenes. So thank you for that. And then, of course, we met Christian. And if you go further in, you can see those too long, don't read notes. And I think that we had a quick question for Christian, if that's okay. I was talking with Ashutosh this week, and I thought what I heard in the last meeting that you were clarifying the limitations of, was it all range support, arbitrary range support? I think I maybe mistyped this. And I was wondering if you could give me a quick 1 or 2 liner.
I think you typed it correctly. It's about P4 DPDK, not BMV2.
Mm-hmm.
So that's what you typed exactly.
Yeah, okay. And is it anything to do with the difference between, the arbitrary range versus the generic range?
Yes.
Okay, so we have
but just for P4 DPDK, not for BMV2.
Got it. Okay.
I don't know what the status is in BMV2, to be honest.
Oh yeah, no, that's fine. I just wanted to make sure that I had it down correctly. Does that work, Ashutosh, for what we were talking about?
Yeah. I think in the meeting you were mentioning that the limitation is in BMV2, and I was clarifying that it's in the P4 DPDK. So I think
okay.
So we have it.
Wonderful.
Okay, good. So we're all good.
Okay.
Then,
So we're all good. Great. Thank you. And so today, what I do have is he's not here quite yet, but Srikanth Kandula. Or first, I'll ask if there are any questions about this. Just the notes that go out. Okay. So today, what I have is Srikanth wanted to come and present regarding the in-network compute API. And so he mentioned that he's about 5 minutes behind because he's dropping off his kid at school. So probably pop on here at some point. Anyway, and then the other items we had were just a few issues that we could go over as well. But it looks like Srikanth has joined. And so Srikanth has been with Microsoft a pretty long time. And he wanted to present today, if you guys don't mind, about the topic we were talking about. Were you ready, Srikanth, or did you need a few minutes?
Good to go, yeah.
Oh, okay, great. So Srikanth, I'm Christina. I'll turn on the camera real quick here. And these are my community of people from various companies, DPU and switch supplier providers. We meet every week, and this is our 110th meeting. And so we work on the Dash APIs and things like that. So we have representation from Intel, AMD, Cisco, Microsoft, Keysight, everybody. And everybody, this is Srikanth.
Hi, thanks everyone. Thanks for inviting me, Christina. I'm just running from a kid's drop off, so I'm a little late. Sorry about that.
No worries.
Let me know when you guys see the slides, and we'll be good to go.
They're coming up for me. I can see.
Cool. This is relatively early work, but the way we are thinking of it is it's joint work with Rishabh, who runs the Sirius program, Deepak, Gerald, and myself. So what we are seeing is we are seeing an increasing adoption of programmable network hardware. This should not be news to this community. We are, just to name a few, there are the Pensando Elbas, the Intel IPUs, the Fungible, the Mellanox Bluefields, and at the same time, there's newer workloads that are coming up. AI ML workloads. And it seems like there will be a change in the kind of traffic or in the dominant traffic that goes on the networks. So part of what we are trying to do is exploit this confluence a little bit. We are hardly the first people to talk about some of the primitives I'm going to describe in the subsequent slides. So sort of where we are coming and why we are coming now is we are not seeing an open API that cleanly separates three things. We want implementations on devices to be clean and clear to a spec. We want the cloud providers to be able to use infrastructure providers to be able to deploy different implementations and make and offer higher primitives on top of that. And we want application libraries like Nickel or RSQL to be able to code at a consistent interface that they can get value from what might be deployed in the network. So this set of objectives we don't feel like is being very well met, and that's where we are kind of coming in. Feel free to raise your hand or jump in with a question.
Okay.
So what transformations, right? We can go over these at like gory detail, but to a first order, we're looking at tried and tested multicast. I don't know how many of you are familiar with the collectives that run in machine learning payload, but here's what's typically called all gather in the top right. There may be 4 GPUs, each of which have different objects, and the job of all gather is effectively a broadcast tree, but it's multiple broadcast trees that are running simultaneously, and there's a barrier because work won't progress until all of these broadcasts succeed. So there's some additional nuance, but if you squint a bit, it looks like a group of you can call them multicast or broadcasts. All reduce kind of builds on top of this. What's happening here is the end result is that each of the GPUs needs a vector sum of parts of things that are coming in from the other GPUs. For example, the left gray here takes all the colored of the same pattern in there. So what's going on here is something like a multicast tree.
Mm-hmm.
But also along the way, the network can do partial sums. So if you implement this literally, each receiver needs to get the other 3 packets. But it might so happen that all 3 packets goes through the same Tor switch, and that Tor switch can just do the gradient sum right there and send only 1 packet further on. So if you think of it, what multicast really protects you is it protects the out link and some of the links on the wire. It reduces the bandwidth usage and maybe also latency because as a correspondence. Whereas in-network aggregations protect the receiver's access path. It kind of reduces incast. It can reduce burst problems and such. There are also a bunch of gradient compression techniques that are coming up. They effectively look like, so you get a tensor in and you get a tensor out, except the tensor out is much smaller. Why can it be smaller? We are seeing 2 main ways that it can be smaller. A lot of these spaces, the tensor spaces, are sparse. So if you might have 1,000 floating point vector, but you could do a principal component analysis on it, or SVD or IVD, and you can reduce this 1,000 component tensor to a much smaller tensor. And the math you need to do this sort of looks like a matrix multiply. So the vector can be it's a column array or a row array, and you multiply it with your compression logic, and out comes a smaller vector, right? We're seeing quite a bit of mileage from this. We're also seeing mileage from just floating point reduction systems. You've probably seen this. Microsoft has a floating point package, but there's FP32, FP16, FP2 even. I think there's some recent results that say, using -1, 0, and 1 gets you as good as Llama with floating points. So there's tricks that we can play here, yeah? And we really want this to be future-proof. And I'll tell you in the next slide how we are encapsulating them all. So we don't really talk about a particular transformation as much as a kind of transformation. Yeah,
looks like we have a hand. Okay.
Yeah, so Srikanth, you talked about the programmable devices which are coming up, right? And most of them are the ones you listed are basically smart NICs, even though they can be used to build a smart switch also, which is the goal of this project. But if you talk about something like all reduce, the transformation has to be done in the network, right? At the TOR switch or even higher up, and not in the NIC, right? So you will need programmable devices which are mostly switch, right? For example, Tofino was one of them, or maybe Broadcom or other switches, right? Silicon One, right? And having it in NIC won't help you unless you actually deploy the smart switches, which have a much bigger footprint in terms of cost and area and all that. So how do you think that the switch community is responding to these requests? Because this is something has to be done switch.
Yeah, great question. Very insightful. So we've seen a bunch of research work, right? Like Tofino 2 style research work. The trade-offs are also clear. We can get into the trade-offs. But to a first order, what we are thinking is that the same open API should span NICs, bag of NIC style smart switches, and pizza box style switches, right? Like the Tofinos, Broadcoms. I think NVIDIA also has a programmable switch. So it'll become a little bit more clearer as we go on. We are trying to be neutral to the device that actually implements it. Yeah. So the only one thing I want to add on the trade-offs, right? We love programmability. I think a bunch of this stuff kind of requires programmability. It's sort of, some of it we can do this in MPUs. The main difference between a NIC form factor and a switch form factor, at least as we are seeing it, is the amount of available memory. And a lot of these transformations are stateless. So multicast is stateless, gradient compression is relatively stateless, but in-network aggregation is stateful. Any of these many-to-one transformations require state. And some of the implementations we've seen don't scale terribly well. For example, if you have a 1 million token LLM going through, my sense is that the tensors that are going to go on the network are probably not going to fit in the couple hundred megabytes of SRAM that a Tofino might have.
Yeah.
But that's a trade-off, right? I mean, that's something for us to work with, not.
Got it, Srikanth. Thank you.
So there's a ton of work that research has done that has these point implementations, which are all great. But the key takeaway there is they're getting good results on Tofino for BERT style models. I would say I've not seen LLM or SLM payload crunched through something like this. And I've also not seen high line rates. We've not seen anything like we've not seen anything like the line rates we are seeing now. Forget the future setups when you presumably have roughly a terabit per second in and out of a 8 GPU box. There's no work we've seen that hits those kind of targets. So there's still some room to. So here are abstraction. So forget the specific transformations. We think of them as one-to-one, one-to-many, or many-to-one. And these are, you should think of these as axioms. You can certainly combine more than one of them. You can chain them. And why should we think of just these three, right? So one-to-one is the basic operation. It takes a packet in or a tensor in and gives a packet out. One-to-many has to do the copy. So here the issue is how many copies do you have a daisy chain? Instead of one processor doing all the copies, can you daisy chain it? But still it's stateless. When a packet comes in, you just deal with it and you move on, right? So many-to-one adds state. If you're doing an in-network aggregation path, the first time a tensor comes in, you don't immediately respond. You kind of buffer it for a bit, waiting for other tensors of similar epoch or similar kind to come. How long you wait becomes a variable, and then you do the vector sum of whatever operation you need, and then you emit it out. But then when you emit, you also have to remind people downstream which vectors got aggregated, because otherwise it becomes. But here also is a protocol logic. Like if you look at Sharp kind of assumes there's a particular tree. And so as long as the tree is correct, the receivers will all are guaranteed to get full packets. But there's a lot of operation in keeping the tree correct at all times. So we feel like that might not be the right idea, because like I don't know if every device is going to implement Sharp, and if you're going to get such rigid end-to-end control on dissemination trees. We prefer a more laissez-faire approach or a more disaggregated approach. So you wait for a bit, you compress whatever you get, and you tell you what you've compressed, and you kind of move on, move the ball going. Does it make sense?
Yeah, so this is where you have to maintain the state, right? Like the device which is doing it has to maintain the state because it has to keep the context alive for X number of packets before it's kind of emits the results. So based on how many flows you're aggregating in up to, you need to have some memory. And once you run out of memory, you can basically go and emit it, right? And start it again. So you don't want a fixed limit of how many tensors you aggregate. You basically saying that should be flexible. And if some devices don't support it, they may even not do it, and the receivers should be able to handle it. So you don't want a fixed topology. You want something like disaggregated. Different devices have different capability, different memories, and the protocol should be able to handle it.
Yeah, that's our preferred approach right now, and
Sure.
that's why we are kind of trying to drive, feedback from groups like you, so that, yeah.
Sure. Okay, thanks.
So we've already talked about this, the first design question, right? Carefully orchestrated paths, very carefully orchestrated. The who aggregates what is also orchestrated. So a lot of this careful orchestration gets you into trouble, because what happens if one of the GPUs is running a little late? Now your network has to keep all the remaining tensors buffered until this last GPU comes through. Whereas something like what Ashutosh said, right? You wait for a bit and you push out. That could help in some cases. That could help overlap computation and communication on the receiver. Maybe the receivers can make partial progress when they get, n minus one of the result, even without waiting for the n. It's not fully clear, right? Especially when you're doing batch gradients. Stochastic gradient descent in a batch mode, you're already paying some ambiguity. It's not fully clear whether you need to wait for the last one. So there's a lot of room here for the network to be a bit best effort, and let the algorithm end-to-end kind of make value out of what comes. Yeah. Another thing we're kind of noodling on, right? And this seems to become quite important for us. You've probably seen the protocol stacks that run in the cloud, right? Amazon has its own protocol stack. Google has one. We have one. We have maybe more than one, depending on which cloud, whether you're doing dedicated or whether you're doing main. So one thing we would like to get is we would like this in-network transformation portion to be somewhat neutral, to be somewhat coexistent with all of these payloads and outer protocols, versus requiring, I'm going to only work on InfiniBand, right? Yeah. So as I said, we're in the very initial stages. So this is sort of like what we are thinking is the basic idea of the protocol. So imagine this is at a message granularity. We're not yet dealing with fragmentation of packets and such. We feel like maybe a jumbo frame should suffice and we can get on with this. But maybe we'll be proven wrong and we'll have to deal with fragments carefully. But the outer packet sort of will be the InfiniBand, the Rocky, whatever else. So where our protocol will come in is there's an ID that identifies the transformation and parameters for the transformation. Now, how these IDs are communicated to the devices, the NICs or the switches, there will be a control protocol and a discovery protocol for the application. We're just now focusing on the data path, right? So data frames will come in like so. Here's a bit more of an example. So some ID that says this is multicast. There might be some group ID in there. And what the group ID translates to in terms of recipients can be control plane determined. For example, if you have a bag of soft NICs, right? So instead of doing a multicast tree among all the purple nodes, you can have these purplish NICs make some sort of a multicast tree. Yeah, the way I'm drawing this, I make it sound like there's a bag of these soft NICs next to each door. And so you get just one copy through the core and one copy on any link, which is good, but it doesn't have to be that way. So one-to-one becomes somewhat simpler. It's stateless. The protocol, the payload just says what transformation is needed, and either a processor just passes it through because it doesn't want to do it, or can't do it, or doesn't have the resources to do it, and whoever does it replaces the tensor data with the replaced one. So this is the more intricate one in this suite of examples. So if you're doing aggregation, you have to say which group of things should be aggregated on, what is the aggregation operation, and which things have been aggregated. So for example, you get an X1 bar, you get an X2 bar, and the operation in this case is average. Average is a commutative and associative operation, so you don't have to maintain all the inputs. You can keep maintaining just one vector's worth of state to represent the result, and you see the result here. And we list the IDs that came in. So if you're following along, right, this does need application change. The application should be aware of these protocols, because in the worst case, no transformation might have happened. Maybe the path did not have any processor, and so there's no improvement, or it might be that only partial improvement was acquired. So the end-to-end application should be, yeah. We have some initial ideas on the control protocol and the discovery protocol as well. Happy to go into detail, but this is roughly where we are at. What do you guys think? Tell us.
Yeah, so Srikanth, you're welcome to this community anytime for comments and follow-ups. And guys, if you have something you want to talk about with Srikanth, I'm curious, what would be a overall use case for this? Like just describe what kind of flow would happen?
Yeah,
Like
yeah.
a workload or just something high level for me?
Yeah. So imagine, so the minimum thing we need is, right, Nickel has to be onboarded, right?
Mhm.
So Nickel gets onboarded, and whenever Nickel runs all gather, right? So Nickel just puts a multicast transformation needed on the 0 packet when it sends it out, right?
Mhm.
And say the network does nothing, nobody else is doing anything. Those packets just go the normal way, unicasted, and go out. Yeah. So there is a small caveat here. Nickel has to know whether or not multicast is even possible.
Mhm.
So that's the discovery protocol. But now instead, say we do have in-network transformers. So say the Sirius stack, right? So say the admin here has implemented, has attached some disaggregated NICs, right? Maybe they attach 2 NICs, 3 NICs, 4 NICs, or some daisy chain of them. And then what happens is once Nickel drops this packet, the network virtualization layer that the provider has incorporated will steer this packet to one or more of this the in-network processors. So this is the control protocol. And when the in-network processor gets it, it implements multicast, right? It looks at the packet and says, this is a multicast packet for this group, which right now happens to be these other GPUs. And so let me make 3 copies of the packet and send them on. And the fact that it made those copies is represented again in the outgoing packet, so that if the path goes through another processor, they're passed through, right?
Yeah.
And the Nickel on the receiver end sees that a multicast has happened.
Srikanth, I have a question because I've been thinking about this as well. How big do you think scale-wise for the distribution trees? Like how many distribution trees do you think would simultaneously need to be supported? Because ultimately this all comes back down, like you said earlier, to memory consumption, right? To track all this information. So at least on this piece, when you're thinking the various distribution trees, how many of those trees do you think there would be simultaneously?
Yeah.
As a benchmark.
Again, great question. So roughly speaking, there's 1 tree per ongoing collective, right? So again, it depends a little bit on the job, how often the job spends its lifetime in a collective versus in GPU. Depends how many collectives are there. Are they the same collective? So roughly speaking, it comes down to the number of either training jobs or inferences running in the cluster.
Yeah, that's what I was thinking. Do you think that let's say for a particular job that the state tree would be persistent over time, like for, that you wouldn't see a variability in the participating nodes change, or do you think it'd be fairly static, or do you see it's going to be a high fluctuation?
Yeah, again, a very great question, right? Very, very great question. So my sense of what happens in the model trainers, the transformer-based trainers, is that they're relatively static modulo failures.
Yeah.
And stragglers. And those can last hours to days. So a jobs tree would be relatively static modulo stragglers. But right now we're also running into cases where the inference itself is multi-GPU, large numbers of GPUs sometimes. And so those trees are probably going to be quite dynamic. Yeah, more dynamic, let's say, more dynamic than the training jobs.
Yeah, that kind of meets the expectations that I was thinking about. Okay, I do. So one kind of comment, a thought around this, and that is for when you were talking about the the actual packet piece for the data plane. So one thing we would want to make sure is that the signaling capability of like the field you had indicated, we'd want to have that fairly close to the front of the packet so that it's easier for the networking device to interpret that this needs some type of network virtualization processing, because there's usually there's limitations across all the various MPUs of how deep in the packet they can look. So we'd want to be able to do that identification in hardware so that we could easily move that into some type of DPU or DPU space in order for additional processing. That'd be my one kind of comment initially around the data plane.
Yeah, that makes a lot of sense. So how early is early enough? Are you thinking?
I think it's got to be. I think most MPUs can at least look into it 100, maybe 160, 180 might be getting a little reach. I'd be happy to get back to you on that.
Gotcha.
I can take that as an action item for you, because there's we see something similar to this same way of how we want to sync, either be able to signal the MPU in order to do the processing piece, and we want to make it sure that the signaling is early enough that it's multiple MPUs could potentially do this function, at least from that standpoint.
Yeah, that makes a lot of sense. So as we are thinking of the protocol, right, the only thing that gets in the way is the outer packet header. Otherwise, we are trying to stick it as early. Yeah.
So depending upon how large your transmit ID field is, it's possibly that can either be replicated into the outer packet. So depending upon the end-cap overlay, there's could be definitely different things we can do to make sure that is done and can be done in a more vendor agnostic way from the MPU. So I'll take the action on to get some of that information for you.
Yeah. So one of the
I also have a.
Yeah, go ahead.
Yeah, I also have a few questions. I think mostly is that how large is usually the size of the gradients, and how many requests do we usually have? So basically, how much traffic load are we looking at for this kind of workload?
Yeah, great question. So the size of the gradients depend on the size of the models. So like a 3 billion parameter model, for example, will have a longer gradient or a shorter gradient than a 7 billion parameter model. I can't give you precise numbers, but that's the rule of thumb. So, and what was the second question?
How many requests per second are we actually looking at?
Yeah. So this also depends a little bit both on the model and the parameter tuning one. Let me point you at a paper. So much of the work that's public on this one uses really older models.
Yep, that's why I was asking. Because I'm aware of the the switch machine learning stuff. For example,
switch ML,
ATPs.
right?
Yeah, switch ML. Yeah. The typical two papers, switch ML, ATP. Though that's ones like did early work. They're mostly on Tofino, and there are other works as well. But the things on that is that they're hitting usually a few issues. The first one is the resource. Right, it has limited memory because they did on the switches. I don't think bandwidth is a problem there. Dash right now is running on the DPU, which means that depends on how much the traffic load is. The bandwidth could kick in place. But of course, we can run it on NPU because model-wise it doesn't really have any restrictions. The other thing is operator. Basically, it's that when we run or reduce, it actually has a depends on the workload, it may run different operators. Some operator is not supported on the NPU at that moment. That means that DPU actually has all the tensor block operators, so that's probably one of the advantage when running on the DPU. MPU will probably have a little bit more limitations over there. The third problem is actually the failover. So basically, say if one switch goes down, right? For example, in the switch ML case, if that switch goes down, your entire rack just goes down. So yeah, so that means that all the gradients then already running on the switch will be lost. That means that pretty much all the workloads needs to restart or retry at least. Yeah, so that's actually my third question is a failover, because I'm not seeing any slides talking about a failover right now. Of course, we are in a very early stage, but just curious, like if there is any requirements that or needs that around the failover story. So yeah, that's basically my three questions. Either traffic load, is a target. Do we aiming for the DPU, or are we aiming for the NPU? And the third one is how do we do the or is there any need to look into the failover case? For example, when doing the mixing the gradients, we actually needs to making sure the gradients are being replicated to another DPUs or another switch. So that's probably a different thing. So yeah, that's all my questions.
Yeah, that's awesome. It's a good set of questions. So for the first one, right? Here's what you already named the right set of papers, right? But just so we know, this is from Switch ML, right? So here are the models that they looked at. Like you were saying, Ref, yeah, they're old. The line rates they're looking at, right?
Yep.
And the key number you're looking for is what is the fraction of communication. So the higher this is, the more this model will benefit from network speed up, right? But there's a lot more nuance that these guys are hiding. So what they're hiding is that they're often hyperparameters that move this percentage. And the way to this is not the right way to look at the problem. The right way to look at the problem is if the network were faster, would your end-to-end be faster for some other parameters in training this model? You see what I mean? If you fix the parameter space, then you're probably not going to, you're optimizing for the wrong thing. So the parameters here could be the batch size, the number of batches, whether or not you're doing, whether you're allowing overlap between communication and computation. So much of this work, I feel, is missing that, right? It's missing with this technology. Here's a Pareto dominant runtime, right? So with ATP, it tries to talk about multiple workloads and stuff like that. It's not fully clear that the results there, yeah. So it's really small scale. So they have one Tofino and they have 9 machines. So to a first order, I would rate Sharp well ahead of both of these works. Because my belief is that Sharp has seen both a greater adoption and a more practical use than either of these. Yeah. And I would, yeah. So that's for the first 2 questions. For the third one, right? Yeah, for sure, failover is really important. But now it depends on a little bit like what do you want, right? If you want a Sharp-like protocol, failover is absolutely critical. But if you want some sort of a disaggregated, the end host will deal with it, style algorithm, then failover is not as important as long as the packets get to the receiver. So somehow we are in that regime, but we know the con for it, right? The con for it is the HPC folk like synchronicity. They like to know everything is highly predictable, and we don't know how much unpredictability will get added because of it. So I would say this is still TBD. We don't fully know, but for sure failover, right? For sure.
Yes, Srikanth, I do like the
Got
idea
it.
of being
Thanks.
able to signal whether a package has had additional processing as it passes through, because that allows an easier case where if there is a failure in the node, essentially then it's business as usual versus getting a speed up, right, by actually having a process, which could reduce some of the complexity of trying to do an HA. And there might be a mix, right? Some operations might lend itself to traditional HA,
Yep.
like for distribution
Yeah,
trees,
because
those kind of pieces.
yeah, since for example, like ATP, if it is missing in a switch, say the switch doesn't have any memory, just send it back to the PS server. So it doesn't really matter that much. It's like always there is a backend that can help you do the thing. There is always a plan B over there. So which is why I'm asking if do we actually have a need to do that, because that's a thing always can catch you up. So
yeah. And like I was saying, that work if it's for tracking on the distribution trees, that's work that's been done in the past, with multicast of how to have redundancy built in. So it could be I think it might be a mix. So it's
that is definitely doable. I think the only thing is that in the papers is very relatively simple environment, so they probably can do whatever they like. In the cloud environment, we will need to think about multiple customers. They have to be probably more isolated, or they cannot step on each other's toe. So that probably will add us a little bit more additional requirements over there or things over there. But I think overall it should be fairly similar.
Yeah, Srikanth, I think Rick brings up a good point, and that is if the assumption is there may be an oversubscribed to the amount of resources in order to do speed up in the processing, then you may get unfair sharing of those resources in a multi-tenant environment, which is obviously something that's of concern. And so then we have to get into some type of load sharing mechanism on top of that, unless you have infinite resources. So that's something we would need to think about as well.
Yeah, it's a great point. Yeah, thanks. Yeah, acknowledged. Yeah, we hadn't thought very deeply about this. Thank you.
Thank you. Yeah, I feels like sooner or later we will look into the in-band aggregation space, because it's actually a very good place to do it. The previous work is all limited by the memory usage and everything, but now we have way more memory than we could use before. Yeah, so it's actually make it a perfect place to do those things. It is very practical.
Yeah, tensors are growing, workloads are growing.
Yeah. That the thing make the aggregation practical is a memory capacity becomes way larger than those days. So yep.
So for further communications, Srikanth, with my community, with you, do you prefer LinkedIn, or just let us know how you want us to talk to you? Or you can always come back to every Wednesday at 9 Pacific. But if there's a way you'd like to incorporate my team's feedback, please let us know.
Yeah, you can, either of those channels work,
Okay.
or if you just send it to Christina, she will Teams me and yell at me to make sure I respond as well. That works too. Yeah.
Right.
Thank you so much for this excellent feedback.
Really
no
appreciate
problem.
it. Yeah. Maybe could you give a quick overview? So Srikanth, you're in Microsoft Research, right? Which, so everyone on the call, this is a different team and organization than mine, but we work together pretty closely. Is that right, Srikanth?
Yeah. So I'm in the networking research group. It's MSR, but a lot of us systems folk work very closely with Azure networking teams. Yeah.
Right. Thank you. And so I'll just do a quick round robin. Were there any other Q&A or discussion for Srikanth before he has to go?
I just want to thank him. I think it's a great topic. It's something, a particularly good use case to develop, whether the process it's in the SmartNIC or in the network. So hopefully we can have a series of this, because I think there's a lot of value, really a lot of value in this.
Thanks, Rob.
Yeah, this is Chris at Keysight. I'd second that motion. It's a real good topic. It's very timely, and there's this AI and ML is all the hotness these days, and it's great to bring this into this community. Thank you.
Yep. Okay. Yep. So thank you, Srikanth. Anything I get, I'll forward to you. And again, you're welcome to come back. I'll forward the series to you just so you can pop in and out. Yeah. Okay, great. I don't know if you guys feel like going over PRs this week. Maybe we could save it for next week, or does anyone have a pressing need or a merge that they need for the repo? Okay, so I'll apply. Thank you, Srikanth. I'll apply the 7-second rule then. Riff, you don't have anything that needs a merge or anything that can't be covered in email?
Yep. Maybe tomorrow's behavior model meeting, we can have a little bit of time to talk about the HA APIs. That's probably, will be nice.
Okay, we'll do that then. So,
sounds good. Thank you.
Thanks everyone for coming. I can give you 10 whole minutes back to get ready for your next meeting. And I'll send meeting notes and I'll make sure I include you, Srikanth, and everyone have a good day.
Thank you.
Okay, thanks.
Bye-bye.
Thank you.
Thank you.
Bye-bye.
Bye.
Thanks, everyone.